Okay, we'll go ahead and get started. Welcome everyone to the CWEA Students and Young Professionals webinar series. My name is Sammy Hunkler and I am a project engineer at Los Angeles County Sanitation Districts. I'm excited to introduce you to our speaker today, Dr. Roger Bales. Professor Bales is a distinguished professor of engineering and a founding faculty member at UC Merced, and has been active in water and climate-related research for over 30 years. He has been a professor at UC Merced since 2003 and an adjunct professor of civil and environmental engineering at UC Berkeley since 2013. His work focuses on California's efforts to build the knowledge base and implement policies that adapt our water supplies, critical ecosystems, and economy to the impacts of climate warming. He works with leaders in state agencies, elected officials, federal land managers, water leaders, non-governmental organizations, and other key decision makers on developing climate solutions for California. Before we begin, I just want to cover some Zoom logistics. During the webinar, please type any questions you have for Professor Bales into the Q&A box you see at the bottom of the Zoom window. If you have any tech issues, you can open the chat box and type in your question. We have Megan Burillo from CWEA staff on the call to help us iron out any tech issues. This webinar is being recorded and will be posted to the CWEA YouTube page. And don't miss these upcoming events by CWEA. How to present on paper and in person for water wastewater jobs on October 15th. And CWEA's virtual conference and expo, October 19th through 23rd. We have a couple events that we think you'd be interested in listed here. And save the date for the annual conference in 2021 in San Diego on April 19th through 22nd. All events are listed on the CWEA events calendar at events.cwea.org. So be sure to mark your calendars and register for some of these awesome events. And with that, I will turn the presentation over to Professor Bales.
Okay, well, I'm really happy to be here, and thanks Sammy and Megan for the invitation. Especially Sammy, you were one of the star students in my water resources class at Berkeley a couple years ago or so. I can't remember how long it's been because time just keeps flying. But thank you for inviting me to give a few comments on my views about California water security shaped by our unique geography and Mediterranean climate here. I start with a picture of wildfire, and I'm sure many of you recognize the location of this. Because there's smoke outside my window right now from the Napa and Santa Cruz fires, but also because wildfire in our natural infrastructure in our wildlands is very important for our water security. So today I'm going to touch on a few topics. I'm going to give a little definition of water security first and then jump into water balance. The only equations I have will be there. Talk about drought, which is a constant feature of our water supply systems, and how we can manage our forests to sustain water security, water supplies. And the key aspect of water security is water storage in a warming climate. So let's start with water security. Just a little context and background. I talk about the 3 I's of water security. We have both natural and built infrastructure all the way through the water cycle. And I think many of the people joining today are on the front lines of keeping that infrastructure running, designing new infrastructure, and making sure we have secure water and wastewater supplies and treatment. We have to have the right institutions, but the foundation is better information, particularly going forward as some of our past practices have got to change because of our warming climate. So there's my definition of water security. It covers both quantity and quality, supply and risks and so forth. And water security is really central and lies at the heart of our adaptation to a changing climate. Now, a second context, a brief history of water resources in California, going from the pre-statehood era to the advent of the huge resource extraction era with the gold mining in the Sierra Nevada and so forth. And the resource extraction era continued for some time as we started making federal investments in water infrastructure, ended with state investments in infrastructure. I'm not sure we're out of the resource extraction era yet, but and then we started in the 70s when I was a student in the early 70s. Sorry, I'm dating myself, but we were all keen to protect the environment, and so we entered sort of the environmental and public trust era, and hopefully we're moving into a period of sustainable resource management with good public support for infrastructure. There's just one thing that's sort of getting in the way of reducing conflicts, and that is climate warming is bringing additional challenges through more extreme weather. So we have these big stresses. As you know, climate has warmed considerably, and we're seeing the effects of it, literally out your window, of a warmer climate. And we have, still very rapid growth in global population. Both of these stresses are linked up with inequality and other issues, and that provides an unprecedented context for our water security systems going forward. So let me go to now the water balance component of this. And I want you to take a look at this photo, which I took a couple weeks ago when I was in the Upper Yuba River Basin in California. These forests are overly dense. So the water balance is different now than it was 100 years ago, because we didn't have these super dense forests that are, you have more trees, you use more water, right? Just like if you plant more tomatoes in your garden, you need to give them more water. So the trees are using much more water, the forest is using much more water than it did, and this dense forest gives high fuel loads, which are one of the factors resulting in more high-intensity wildfire. So now the water balance, just a second. I'm at home, so people are coming and going here, including the dog. Back to the water balance. This is water balance for the statewide, California. Precipitation is averages about 200 million acre feet per year, and I hope everybody's familiar with the term million acre feet. Acre foot's acre area foot deep. And the applied water, which is this circle in the middle, is about 80 million acre feet. The difference between those is the water use for our natural ecosystems that are the sources of much of the water that the state uses. And so we typically talk about agriculture being 80% urban, 20% of the state's water use. That's the bottom half of the circle. The other half of this 80 million acre feet stays in the aquatic environment. So that's the average water balance. Obviously, it differs quite a bit from year to year, But when people talk about, well, we got to move water from this top part of the circle, take it out of the delta flows and so forth and put it into agriculture, I say, hey, look at the difference between these two numbers, precipitation and applied water. Our overly dense, overstocked forests are using quite a bit of water compared to what they did a century ago. So again, I'm going to plunge a little deeper into the water balance here. So here's my equation, precipitation equals evapotranspiration, that is water use, evaporation and water use by vegetation, dominated by transpiration in the natural ecosystems, plus runoff, plus change in storage. And storage is key to both our water security and our ecosystems. So keep that equation in mind as we go through here. This is Sierra Nevada precipitation. So I've cut out the Sierra Nevada here. And precipitation increases as you go from the south to the north. So we have, as much as 3 times as much precipitation in northern Sierra as in the south. On the other hand, snowpack increases as you go south. So the mountains are higher in the south, so that means we get much more rain dominated in the north and snow dominated in the south. So that's part of how our geography and climate interact with each other. Now, let's look at the water balance across the major river basins draining the Sierra Nevada. And I'm really focusing on the Sierra Nevada here because that's where more than 60% of our water supply comes from. I've turned the state on a side here, and so north is pointing up to the left, partly because it fits on the slide better, and partly because then all the Sierra Nevada and Central Valley drains down to San Francisco Bay here. Yeah. So again, our water balance, and here we show that the 13 of the major rivers draining the Sierra Nevada from the Feather River in the north down to the Kern River in the south. And the total height of the bar is the precipitation. So I said precipitation on average increases from south to north. The Feather doesn't quite follow that because there's a rain shadow up there, but let's not worry about that for now. Because Sumnus doesn't fit it because it's a lower elevation basin. And then the bottom part of the bar, shaded green, is precipitation minus runoff, or the, quote, evapotranspiration. Now, over a long period of time, change in storage is 0, and this is a multi-year average, so delta S is 0. And one can see that evapotranspiration doesn't vary as much from year to year as does runoff. Why is this? Well, the forests and grasslands and savannas in the Sierra Nevada need about the same amount of water every year. That is, and so it's the runoff that varies as precipitation minus evapotranspiration. So the forest takes its cut of the water first, and what's left over is runoff. So that's part of the water balance. So the result is that there's much more precipitation and runoff in the northern part of the state, north of the Sacramento-San Joaquin Delta, but much more water use south of the Delta for agriculture in the San Joaquin Valley and for the urban areas in South Coastal California. So thus, movement of water through the Sierra Nevada. Now let's take a little deeper look at that water balance. And I've listed the 13 basins here, Feather through the Kern. I've added one more basin on the left, the Shasta Basin in the far north. And one can see, first of all, on the top panel, each bar represents As we go, elevation is on the vertical axis, and the fraction of precipitation is the total height of these blue bars. So we can see precipitation generally increases as you go up in elevation. And the yellow shaded part is the evapotranspiration. And it peaks in the middle range, middle elevation of these basins. So I've overlaid evapotranspiration on top of precipitation to show what fraction of the precipitation leaves as evapotranspiration by elevation from 0 to 4 kilometers elevation. Now, the evapotranspiration is lower at the lower elevations because of the lack of water. Basically, there's two terms to the water balance. Precipitation equals evapotranspiration at these lower elevations. Most of the runoff comes from the higher elevations, and I've showed the snow line here. So most of the runoff comes from the snow zone in the higher elevations. And then you see evapotranspiration drops off at these basins as you go to the higher elevations. Why? Well, because it's too cold. The trees don't grow year-round. They shut down in the winter. So in the middle, near the rain-snow transition, is this happy zone for trees where it's not too dry and not too cold, and we get the maximum evapotranspiration. And above that peak, where precipitation increases and evapotranspiration decreases, is where we get our runoff. So that's an important part of California's water supply, is the elevations above the rain-snow transition. The snow zone provides most of our runoff. Then you say, as well, what's happening when the climate warms? The snow zone's going to go up. Yeah, and the evapotranspiration will increase as well. There could be a slight feedback with CO2 enrichment, but I think the temperatures are warming in advance of significant CO2 enrichment right now. So you say, well, that's millimeters of water for this top part, or fraction of precipitation. If we look at actual runoff, we need to weight it by the watershed area. And you can see in the Southern Sierra, the basins like the San Joaquin and the Kings are mostly high elevation basins. You've got the Cosumnes, low elevation, Yuba and American, so mid-elevation basins, and then lower elevation in the north. So when we do that weighting, we can see clearly that much of the runoff volume-wise, which is on the fraction of volume on the lower pile, does come from the higher elevations. So that we keep that in mind. The Kings, San Joaquin, these basins are probably less vulnerable to climate warming versus places like the Feather, Yuba, American, where significant runoff is at the rain-snow transition. You move that up a little bit, you're going to get rain, and you're going to get longer growing seasons. Okay, so when we talk about adapting to climate change, we're talking about managing ecosystem services, which means managing water. It is managing forests, managing wildlands, basically managing evapotranspiration. So we don't necessarily want to see these top parts of these bars shrink if we want water supply for our economy and agriculture livelihoods and urban areas and so forth, which means these green bars, if they increase, then we have the trade-off, assuming precipitation remains about the same. So now let me say something about what I call the recent experiment, which is the 2011, the drought that started in fall 2011. It was water year 2012, but it started in fall 2011 and nominally ended in fall of 2015 when we got a near average precipitation winter. What happened was we had massive tree mortality. Now let me say a little bit more about drought vulnerability. Again, the Sierra Nevada snowpack is very important for our runoff. If you look at a quote average year, this is a satellite image. So what you're seeing is snow-covered area around the canonical peak accumulation, April 1st, compared to a drought year, much different, and that average year, 2016. So there are many indices of lower water supply and drought, but let's look at this other issue that's going on. Both 2011 and 2017 were really wet years. We got a lot way above average precipitation in the Sierra Nevada. In fact, 2017 had more precipitation than 2011. But when you look at these pictures, if you squint a little bit, you can see that the snow line was actually higher in 2017 than it was in 2011. Now, why was that? Well, we're getting warmer droughts. I mean, we're getting not just warmer droughts, but warmer wet years too. So we're getting more rain and less snow going forward. And that's a reality of our water supply. Now, this snowpack has been central to the state's seasonal water storage. Since the state was developed for agriculture and urban activities. We depend on the storage in the snowpack during the winter and then the runoff in spring for downstream uses. So these snow line changes reflect temperature increases and lost snow. And a major question is, how do we make up for that lost snow given these changes and the elevation patterns and precipitation patterns that we have? So I just want to point out that extremes of the past are not a sufficient guide to the future going forward. So let's just take a look at a couple of drought issues. If you remember back 2011, we had a wet year, and then it started drying out so that by November 2012, 13, 14, 15, it became progressively drier. Then we started to break the drought, and here's where we are now in August 2020. We have severe drought in the northern part of the state and more average conditions or abnormally dry in the southern part of the state in terms of precipitation and soil moisture. Now, if we look over longer time periods based on tree ring records, was this drought of this recent 4-year drought an anomaly? And this shows from the year 900 up through about 2010, the reconstructed runoff in the San Joaquin River. It would look similar in the Sacramento River, the major rivers draining the Sierra Nevada. And so the horizontal lines are at the average, and you can see years that are below average. So the longest below average dry period was 13 years. Seems to me that's a little bit longer than the recent drought that we had. And I would say that we're probably ill prepared for that long and dry period because we depend on over-year storage of water for making up precipitation deficits during droughts. And we see some pretty long periods that may have just a 1 or 2 year break in the dry period. And we see these 4-year droughts at least one per century and sometimes multiple ones per century in this record. So that's partially a guide, but it's not enough of a guide because remember the temperature effect. When we look at temperatures of the past 110 or so years based on instrumental records, let's divide all the annual temperatures statewide into 4 quadrants. Temperature and precipitation. Was it wet and cold, whoops, was it dry and cold, wet and hot, or dry and hot? And these yellow circles are all the years since the year 2000. The red circles are all the years. The yellow ones, which I put over top, and you can see all the yellow circles are well above the average temperature, which is this horizontal line, and many of them are left of the average precipitation, which puts them in the hot and dry quadrant. The drought years are typically up here. The recent drought years way up here off scale. That is, we have unprecedented dry periods. Now, what's happening, on top of that 4-year drought, which helped us learn a little bit more about our systems, was this century-long experiment of suppressing fire. As you probably are aware, in the Sierra Nevada and other forests of the state, Southern California forests, North Coast forests, there's been fire suppression to protect private property, infrastructure, public infrastructure, private infrastructure, and so forth, meaning that a forest of 1896 looked like the picture on the left. A forest, approaching the year 2000 looked like this on the right. Some of our forests have 5 or 6 times the number of trees as they did 100 years earlier, and at least double the biomass because there's a lot of small trees. Historical forests tended to be large, mature trees. Current forests, lots of smaller trees replacing them. So we know that was a bad idea, and sustainable solutions remain somewhat elusive. So in terms of going back and forth between water supply and forests, this is what happens to our forest when we have overstocked forests and multi-year dry periods. This happens to be near one of our research sites in the southern Sierra. And if you look across the southern Sierra, in areas where precipitation exceeded evapotranspiration for 4 years, and in some cases it was up to 1.5 meters of these red areas, that is, precipitation was 1.5 meters less than the water demand of the forest, that's where you saw the dead trees. And this is based on aerial surveys done by the Forest Service. So tree mortality occurred when you had drawdown. Now there is storage, and I want to hit on the storage theme for a little while as a way to offset our unique, quote, geography and climate. Roots go down quite far in the subsurface, and you can have water, root accessible water, down several meters. In this case, at this site where there was massive tree mortality, there was over 1,000 millimeters of drawdown during the drought. That is, at the end of the drought, there was about 1 meter less water spread over the top, 5 or 10 meters than there was at the beginning of the drought. And it recovered afterwards. Well, when it got down this far, the roots could no longer reach the water, and the trees died, basically. They died due to pests, but they were stressed by that. So this is linked in with our management of our natural infrastructure for the state's water supply. The climate solution is forest thinning. You take those overstocked forests like you see in the background of this picture, and you reduce the number of trees using water. In this case, they've been ground up as mulch and they're on the forest floor. What you're seeing here is a more historical forest density, although smaller trees than you would have had historically in this forest in the American River Basin. So managing the forest water balance is one of our climate solutions and water solutions going forward. So again, think about the water balance. It's this evapotranspiration component that balances off with runoff. Now, fortunately, there's multiple, well, let's just say, let me come back to fire in a minute, but tree mortality. So if you have tree mortality, you get more runoff because, and that happened in the Kings River Basin and the Southern Sierra where there was massive tree mortality. But it's not the sort of forest management that we want. We want more going from this on the right to this on the left. That is thinning that retains other ecosystem services in the forest, other multiple uses of the forest. And we certainly don't want these wildfires in overstocked forests because that screws up many uses, creates water quality problems downstream, and so forth. But fire does, reduce evapotranspiration, and you get more runoff. But it's not the way we want it to achieve that. So fortunately, there's strong interest in the state in thinning these forests to reduce the risk of high intensity wildfire. And a side benefit is that you reduce water use when you do things like this. If you read the article by Paul Rogers in the San Jose Mercury News last Sunday, he reported on an agreement between the state and the U.S. Forest Service to invest in thinning 1 million acres per year in the state. And I think they were including, forests, chaparral, grasslands, or savannas, and so forth. That's a significant commitment. You know how much it costs to do an acre of thinning, like on the left? Well over $1,000 an acre for restoration. So you do the math. If you're going to thin $1 million a year, I think they just signed an MOU to commit to over $1 billion a year. So if we look at some of these river basins, like the American River Basin, they've had 5 large wildfires in the last 30 years. I've outlined them with yellow polygons here. Much of this, with the big King Fire from a few years ago being the largest, that's not a way to manage our natural infrastructure. So, but we can use the wildfire lessons to plan and verify the water benefits from forest treatments. So if we look at forest water use, evapotranspiration, 600 millimeters per year is a good average number of how much water use there is by the forest. What's the average precipitation in Sierra Nevada? Maybe a meter per year or something like that. Same as the global average. When you have high severity wildfire, you drop that water use significantly. Low severity, a little less. And then over time, vegetation grows back and you start using more water again. So I think we're looking at a pattern here of needing to go in and spend, the commitment by the state and the Forest Service was a 10-year commitment for 1 million acres a year. After that, hopefully it can be a little bit less per year, but it's still going to have to be significant forest treatments. So there are thinning projects going on right now, particularly in the highly productive American and Yuba river basins, where if you thin forests, you really do get a lot of runoff coming down. And this is in the Stanislaus National Forest and Experimental Forest, where you actually still had some mature trees. And you can see the contrast between the treated, restoring it to a historical forest in the foreground, and an untreated or current conditions in the background. So I want to go to the last item on here, which is water storage in a warming climate. I've talked about the importance of storage for forests, and of course that storage contributes to base flow and runoff and so forth. I want to touch on storage in a broader sense now. the state depends on this upper watershed storage to meet our seasonal water demands. The snowpack is important. Equally important is the water stored subsurface in the upper watersheds. And then we have dams that store water. And on average, we have about 1 or 1.5 years of average rainfall and snowpack storage in our reservoirs. Not enough to get through a 4-year drought. So we're looking to groundwater aquifers as water banks, as places to store water. And that, so let's think about the use of dams, because when I talk to colleagues in the Central Valley, they say, let's build a dam and we'll have more water. Well, I say, yeah, wait a minute here. You got to have the runoff, and you got to put it in the right place and so forth if you're going to do that. But and let's look at other solutions as well. So this is a little bit involved, but let me walk you through it real quick here. Runoff is this blue line on the top for current conditions. That is, runoff peaks in the spring when the snow melts coming out of Sierra Nevada. Water demand is this red line, which agriculture use peaks in the summer. And the difference is the water you need to store, the runoff you need to store in order to meet the water demand. And then you release from storage over here. You can't store all the water because you have to provide some flood storage capacity in case you get a big rainstorm in May or something. And right now we have a structural shortage. That is, we're using more water than is replenished every year, so we're drawing down our groundwater. I think people have seen that in the news or in your professional work. Moving forward to projected conditions in a warmer climate, which we're starting to see already, earlier runoff. This peak is no longer in the spring, it's in the winter because we're getting more rain. Which means, water demand is actually maybe shifted a little bit to the right because we're getting rain in the agriculture areas too. So we have a larger imbalance between runoff and demand for water storage, but we need to have more flood storage capacity because of the the earlier runoff and the fact that we'd have less snowpack storage. And we can project, therefore, larger shortages if we're getting less water. So how do we deal with that? Well, the state is looking at managed aquifer recharge. That is, there's agricultural areas below most of these rivers coming out of the Sierra Nevada. There's active farmland that can be flooded for infiltration, as long as it's not flooded for too long and to damage the crops. There's many crops that can take that and recharge water, as well as recharge basins. Fallowed fields can act as recharge areas. So we need more recharge of groundwater. Then we can use groundwater as a multi-year storage. We get lots of single wet years plus the dry years. So in these wet years, we get high peaks. Looking at stream flow from the American River Basin from October of one year through the next October. Historically, the peaks are like the gray line, projected with more rain, less snow, higher peaks. So we have to capture those peaks. Can't capture all of the peaks, but we can capture some of them and recharge the groundwater and use groundwater banking. Is the current direction the state is looking at, but looking at it a little bit slowly right now because it does take investment to put these facilities in place. You need to get the water to the land, to the right land, and you need to be able to monitor and then extract the water and so forth. I am optimistic. let's see, how's the time? Okay, one more thought before I go. I think I still have a minute or two. Stop me if I need to wrap up, Sammy. Educating our communities about water and climate is central to water security. It's one thing I spend a lot of time on these days. This is a satellite image of Western US. Obviously, here's the Central Valley and Sierra Nevada. But I want to focus over here in a little further east. So seasonal snow has been central to our water security for centuries. And I want to zoom in on the Four Corners area. Some of you have probably been to the Four Corners, the corner of 4 states, Utah, Colorado, Arizona, New Mexico. And the Hopi have lived there for centuries. In Four Corners area, they depend on seasonal snowpack. And so, we can learn a little bit from how they managed their water supplies and educated their community. Sitting on my mantle are these Hopi snow maidens. Now, some of you have probably seen various snow maidens, and they had a festival every year. It was partly maybe religious, but largely educational. That's how the elders educated the children about the importance of the seasons and of the snowpack, and the water supplies that they depended on for their agriculture. So we need ways to educate our communities. Now, I don't think the Hopi Snow Maiden are going to work in San Francisco or Los Angeles, but I have been involved with a nonprofit filmmaker. I think I provided links to these 2 films. If not, email me and I'll get it to you. This is the filmmaker's website. Beyond the Brink covers some of the topics I touched on today. It's a water food security film. Beyond the Brink, California's watersheds, more about the Sierra Nevada watershed. And it's actually showing on PBS right now nationwide. Throw out some of my favorite reading on the topic of water if you want to delve deeper into some of the stuff I've talked about. Of course, Cadillac Desert's the canonical book. I love the new book by Mark Arax. Again, sort of history of the Central Valley water from a journalist perspective. And if you like science fiction, you can't beat The Water Knife by Paolo Bastigalupi. And it's a little bit, out there, but not completely unrealistic. So, main points, and I'll wrap up here. Water security, infrastructure, institutions, information overlaid with climate. That's how we adapt our economy to the climate and geography that we have here. Water balance and managing evapotranspiration. Do we want the evapotranspiration in our forests? And do we want to manage it, or do we want the evapotranspiration in our agriculture areas? Drought vulnerability. Plan for longer, hotter events because they're coming. Managing forest water balance. Let's take a multi-benefit approach, not just let tree mortality due to fire and drought shape our forests. Let's make the investments needed. And water storage in a warming climate. Groundwater plus flood containment. We can solve 2 problems with one solution here. So that's where I am. I'll turn it back to you, Sammy, if you want to have some discussion. Thanks everybody for your attention and interest.
Thanks so much, Dr. Bales, for the informative presentation. You always have the best visuals, and I like that some of the photos are actually taken by you. That's really great. It looks like we have 2 questions. The first one is, what evidence is there that a more thinly treed forest leads to a peakier spring melt? I'm thinking the trees provide shade, thus allowing the melt and making a dam operator's life easier.
Yeah, there's a trade-off there. So If you thin it too much, then you will get earlier snowmelt, such as you would get with, say, a wildfire. But if you don't thin it very much, you won't get much change in melt. But in between, there's a just right forest density where there's enough shade so that the low angle winter sun doesn't melt the snow, and the trees that are there, of course, they absorb sunlight and re-emit it as heat. They don't melt the snow. So you can gain a couple of weeks of extra storage by strategically thinning the forest. Now, fortunately, that strategic thinning aligns pretty well with what you need to do for reducing the risk of high severity wildfire. So that's good. That's good.
Great, thank you. The second question is, how receptive are Central Valley farmers and other ag operators to receiving floodwaters to recharge groundwater? I've heard of some great successes, but I imagine there is resistance.
I would say there's skepticism. I spent I spent a day with one farmer up in the Sacramento Valley, and he said, yeah, we can put water on our, I think it was pistachios for longer, almonds for a shorter period of time, and walnuts not at all. There's been flooding of vineyards for several years in some areas. There's actually overflow basins even up in the Russian River, where some vineyards are set up. And again, the time period has to be the right time of year and not too long. I think it gets down to financial incentives. If you're partnering with a farm operator, the operators or owner, they're taking some risk. There's public benefit. So you look at where the benefits are coming from, and you try to you compensate. And that carries over to managing all of our natural infrastructure. I consider groundwater recharge on ag land to be a combination of natural infrastructure and built infrastructure. And so the beneficiaries who are the larger ag community need to work out an agreement with the person whose land is being used for that, and there's mechanisms to do that. There's other mechanisms that are happening in terms of financial incentives over in the Santa Cruz area. There is a pumping fee. Every time you pump water out to irrigate your cane fruit, your raspberries or blackberries and so forth, you pay a fee for pumping the groundwater out. But if you set aside some of your land and recharge water, you get a credit. And I think that's a great market solution. So we need to look for more clever solutions like that to engage more landowners. Yeah, and then you get to forest thinning in the Sierra Nevada. We're involved in a couple of projects where the water supply and hydropower operators are actually paying for forest restoration on Forest Service land, because that's their headwaters. They don't own the land, but they get the water from it. And some of these hydropower and water supply agencies sell the water twice, once as electricity and once as ag and urban supply water. So there are, I think, plenty of incentives out there to address groundwater recharge, forest restoration, and other natural infrastructure investments, or some people call them green infrastructure, that we need to make to shape our state's water to the needs of our economy, environment, and including disadvantaged communities.
Great, thank you so much. So it looks like we have another question. What agencies / parties do you think carry the most responsibility to implement these kinds of projects? Does a top-down approach from the state have the highest chance for success in your opinion?
If you want a short answer to the second question, no. Yeah, it takes partnerships. And for example, on these some of these forest management projects, you need the landowner. Well, the U.S. Forest Service, if you think that Congress is going to allocate $1 billion a year for forest restoration, you probably think you're going to win the lottery too, tomorrow. So it takes partners, it takes beneficiaries getting together. Now, who are the beneficiaries that can come together to do this? Well, there's obviously the water interests, there's the hydroelectricity interest, there's also the interests of people who want to lower the risk to their infrastructure. There's a lot of public infrastructure that is at risk. I've talked to colleagues in Placer County, they say, yeah, we have $8 billion worth of infrastructure at risk of high severity wildfires. Of course we want to reduce the risk of wildfire. It's a no-brainer. We don't need to do the cost-benefit analysis. And then there's the people of the state. If I step outside, I'll be breathing pretty bad air quality right now. And if some of you are in the Bay Area, you know what I mean. So we benefit. So the state should be a partner in this. Who leads? I think it needs lots of regional coalitions to lead on this, and there's willing partners. You need a catalyst to pull the partners together, a credible catalyst. The state can help there and maybe provide funding to get things going, and provide some of the funding to eliminate some of the barriers to getting people together, and provide some of the funding, but beneficiaries have to provide other funding. And there are good financing mechanisms that are available to do that. NGOs are also important there.
The next question is, how do you think the elimination of ocean discharge will help the state's water table?
Well, I think it's great to see that cities like Los Angeles, municipal areas like Los Angeles, are going to greater water reclamation. Back before I got my PhD, I was actually a consulting engineer with a firm in Pasadena, and worked on water reclamation projects, among other things. And he kept asking the question, why can't we do more? Why can't we do more? Oh, it's too difficult, and so forth. Yeah. So I'm really glad to see finally now people doing more. Local resiliency is very important, and that provides local resiliency, which can help offset some of these reductions that are likely to occur in the imported water supplies going forward. So I think it's really important to provide that local resiliency. Now I know Los Angeles needs to find groundwater storage, so you got to first maybe decontaminate some of the groundwater basins before you can do that. So that's a challenge also.
The next question is, how unusual is the flurry of lightning strikes, thousands, that occurred last week in central and northern coastal California? Resulting fires even overwhelm thinning efforts.
Yeah, I think it's unprecedented for the state, given our current level of development and importance of fire suppression to protect infrastructure. I have a friend who's studied lightning for decades. It's his company, and I never remember any conversation with him about this density and frequency of lightning strikes in the Western U.S. Especially but it's not only the lightning strikes, but also the the dry fuel, the amount of fuel available and the dryness of the fuel. So I'm sure there have been instances of frequent lightning strikes like this, somewhere in the state or in the West in past years. But it's the combination of events. We do expect a more vigorous climate, precipitation, lightning, evapotranspiration, speeding up our climate cycle as we get warmer, and that's what's happening now. It happens to hurricanes too. So I don't know how unprecedented it is, but it's like the last 4-year drought. It's at the end of the distribution.
Great. Well, I don't see any more questions, and we're pretty much right at time. So thank you again so much, Dr. Bales. We really appreciate having you. We appreciate you sharing your knowledge and providing us with a really interesting webinar today.
Thanks for inviting me, and good luck with the rest of your series, and good luck managing California's water security.
Thanks.